There are over 100 elements in the universe, and 81 of them are metals. Some of these elements are extremely reactive. Some immediately react when they are exposed to other substances. Some explode when you shine a light on them. Which are the most ferocious elements? That's coming up, but let's start with the elements which are so unreactive that they won't change for hundreds, thousands, or even millions of years. They might sound boring, but they have their uses.
This is the famous Portobello Road market in London, home to all sorts of craftspeople and artists. The great thing is there are lots of people here selling jewellery, which I adore. Now, the metals used in jewellery can tell us a lot about the properties of these particular elements in the periodic table. For example, I've got some gold rings here. Now, gold is also known as a precious metal and can be easily used to make jewellery. I'm wearing a copper bracelet. Now, copper has this lovely golden brown colour and can also be used to make all sorts of different things. My earrings are made of silver. Now, silver's a great metal for making jewellery because it can be easily shaped and moulded to make all sorts of tiny, tiny little shapes. Now, the gold, the silver and the copper are examples of just 3 elements in the periodic table. There are over 100 different elements in the periodic table.
All the elements are grouped together in the periodic table. Those shown in green are non-metals. The majority are metals, shown in blue. The metals used in jewellery, copper, silver and gold, are all found in the same group of the periodic table. They are a family of elements and, like most families, they've got a lot in common.
The most obvious thing about these metals is that they are unreactive. If they weren't, they'd react with the air. In fact, copper and silver do tarnish over time. That's because they react very slowly with air, but they can be easily polished again. Do you mind if I try one of these on?
No, not at all. Here. Yeah, hold your hand out flat. That's it. Over your thumb. There we go. You're in.
That's lovely. Is that really made out of forks?
Oh yeah, indeed. It's all made from recycled cutlery.
And is this made out of real silver?
No, that one is silver plated. These ones are silver plated, and these ones up here are all solid silver.
Have you got anything where we can see what's underneath the silver plating?
Yeah, indeed, yeah. You can see on this, where the silver's worn through, the copper's starting to show through.
So that brown metal is actually copper?
Yeah.
If you had a choice, what metal would you prefer to work with?
Silver, all the time. Beautiful, yeah.
Why would you work with silver?
It's soft, malleable, and, just altogether easier to work with. And it feels warm as well. It's lovely.
Not all the metals in the periodic table are unreactive. Some react in air, some even burn in air. So you won't necessarily find these metals on their own in nature. You're more likely to find them as compounds or as some of these beautiful crystals. Murray, this looks really unusual. Can you tell me what that's made of?
Yeah, this is iron pyrites. So the common name is fool's gold. It's a compound of iron and sulphur, and it's formed naturally in these cubes.
And why is it called fool's gold?
Well, if you look at it, you can see the goldy colour. In olden times, people thought it was gold.
And I can't believe that it actually naturally occurs in these shapes.
Yes, it forms natural cubes just like this, and they all interlock, as you can see.
Now, if that was made of just iron on its own, it would be very rusty by now, wouldn't it?
It would be, but the sulphur stabilises it.
Now, do you have anything that has either sodium or lithium or both of them in it?
Yes, I do. This is literally a space rock, and it landed in 1947, and it contains some of the trace elements are lithium and iridium. So with very high iron content, these meteorites are magnetic.
That's great. And that's because of the iron?
It's purely because of the iron in the meteorite, yes.
Thank you very much.
From the unreactive metals, we move to the more reactive ones. The most reactive metals can be found in Group 1 of the periodic table. They're called the alkali metals. The ones you've probably heard of are lithium, sodium, potassium, rubidium, and cesium. And you've probably seen many of the reactions of lithium, sodium, and potassium in school. Lithium is reactive, so it's usually stored under oil to keep it away from oxygen in the air. It can be cut with a sharp knife to reveal the shiny metal inside. Sodium is similar. Again, it's stored under oil and can be cut slightly more easily with a knife. Potassium is also stored under oil, and it cuts even easier with a knife. Obviously, there are huge similarities here, so you might expect rubidium to be kept well away from the air. In fact, it is, but instead of being under oil, it's stored in a sealed glass container which has had the oxygen removed. So, what about cesium? Based on what we've seen from the other elements in this group, you'd expect it to react with oxygen, and it's probably easier or softer to cut than the others. It's also stored in a sealed glass container in order to keep oxygen well away from it, and in fact, the heat from your hand is enough to melt it. As we go down the group, the melting point of each element decreases.
I love pretzels, especially the one with these lovely crystals on them. These crystals are salt crystals made from sodium and chlorine, both of which are highly reactive elements.
This is a lump of sodium. When it gets really hot, it melts. If you mix it with a jar of chlorine, a reaction immediately takes place to form sodium chloride, or common salt. As a family, all alkaline metals form chlorides with similar formulas. Many of the alkali metal compounds produce flame colours. These can be used in fireworks. This spray contains a lithium salt dissolved in water. Lithium produces a brilliant red flame test. Sodium, a yellow flame. Potassium, a lilac flame. And rubidium and cesium are also lilac.
Now, like all family members, not all the elements in the periodic table are identical in the way they behave. One thing you'll notice as you go down group 1 is there are definite trends, just like we saw with melting points. The most obvious trend in group 1 is the reaction of these elements with water.
This is lithium reacting with water, a reaction you've probably seen in class. It's releasing hydrogen bubbles. That's why it's fizzing. This is sodium. The reaction with water produces so much heat that it's melting the sodium. And this is potassium. In this case, the gas ignites as well. So, any bets on how rubidium will react with water? And finally, here's cesium. So, there's no doubt that as we go down group 1, reactivity increases. Lithium is reactive, but cesium is extremely reactive.
This crystal is known as fluorite. Fluorite is a combination of calcium and fluorine. Calcium is a metal and fluorine is a non-metal. Fluorine can be found in group 7 of the periodic table. Group 7 is known as the halogens. This non-stick pan is coated with a chemical that contains fluorine. Now, fluorine is a poisonous gas, but when you combine it with other elements, it is actually safe enough to eat off, and it is even contained in drinking water.
Like the group 1 metals, there are similarities and trends as you go down the group. They are all non-metals. They are all coloured and they gradually change from gases to liquid to solid as we go down the group. Fluorine is a yellow gas. Chlorine is green. Bromine is a dark orange liquid with an orange vapour, and iodine is a dark purple solid which, if gently warmed, produces a violet vapour.
It's incredible how something as potentially nasty as fluorine can be made into some really useful everyday products like fluoride toothpaste. Now, just how nasty is fluorine? Professor Holloway from the Leicester University Chemistry Department is an expert on fluorine and its reactions.
The fluorine is stored in a gas cylinder and it's released through the nozzle.
Fluorine onto roll sulphur.
The flame is caused by the fluorine reacting with the sulphur.
Now we have wood charcoal, carbon, and fluorine reacting with that, and it will burn away. So with iron wool you should get instantaneous reaction again.
Fluorine bursts into flames when it reacts with many other substances. It even reacts with other halogens, like iodine. So, how does the reactivity of fluorine compare to the other halogens in group 7? A simple way to demonstrate this is to see how the halogens react with hydrogen. Hydrogen and iodine react very slowly, so let's try the next halogen up the group. This gas jar contains an equal measure of hydrogen and bromine. There's no reaction unless you put a lighted splint in the mixture. This plastic bag contains an equal mixture of hydrogen and chlorine, but it doesn't react unless you shine a bright light on it. So, any predictions about hydrogen and fluorine? This balloon contains hydrogen and fluorine is directed at it. The reactions with hydrogen clearly show that the reactivity of the halogens increase as you go up the group. Fluorine is the most reactive non-metal in the periodic table.
The halogens have lots of uses and the products are well known. For fluorine, there's toothpaste, non-stick pans and Gore-Tex jackets. For chlorine, there's plastic, bleach, disinfectant, water purification tablets and antiseptic cream. For bromine, there's photographic film, halogen lamp bulbs and asthma medicine. And iodine can be used as an antiseptic. Most halogens have bleaching effects as well. Now here's something I tried earlier on a pair of jeans. This isn't something that should be attempted without the appropriate protective clothing. A drop of neat bleach on your skin or in your eye can be very damaging. After a few minutes, the dye in the jeans starts to bleach. And to prove it is the chlorine in the bleach that is involved in the bleaching, we wet a piece of material and add it to the boiling tube of chlorine. An hour later, it was completely discoloured.
The periodic table is an ingenious way of organising the elements. Not only does it bring together families of elements which are similar, but it also allows us to predict some of their properties. So, if you're looking for the most ferocious metals, try the bottom of group 1. Or, for the most vicious non-metals, look at the other end of the table at the top of group 7. So, what do you think will happen if you react cesium with fluorine?